Right, remember I was going to mention evidence specifically for one of the other models. So redshift is evidence that supports both the Big Bang and the steady state model, but CMBR, which is cosmic microwave background radiation, okay, is only evidence for the Big Bang. Okay, so remember at the start of time, okay, it states that we have a huge amount of energy due to the expansion being caused, okay, the universe expanding. So that energy needs to come from somewhere, and wherever it came from, that initial energy would have been a very high frequency wave, okay? And over time, as the universe expanded and cooled down, that high frequency wave would have stretched out to the microwave wavelength. And if you remember back to a previous video, radio waves have got the longest wavelength. Okay, then microwaves come next, and then gamma waves are literally the highest frequency wavelength. Okay, highest frequency waves in the EM spectrum. Okay, so essentially over time, approximately 13.7 billion years, that original radiation has spread out, stretched out to the microwave wavelength. Okay. And this is an interesting point here. In 1 billion years' time, CMBR could become a radio wave radiation. Okay, so please note it is simply the stretching out of that initial high frequency radiation at the start of time. Right, so remember redshift supports both the steady state and the Big Bang model. And one interesting thing is that astronomers have indeed observed that all galaxies do show redshift. They do appear to be redshifted, and the faster ones do appear to be having a wavelength that is more redshifted compared to the slower ones, okay? And that is in proportion with the distance that they are from our Earth, okay? So the further we look into our universe, okay, the greater the redshift is for the ones further away, and they are actually moving faster, okay? So please make sure if you see this in an exam, okay, so you need to state that if the universe is expanding, how does redshift support this? Well, all galaxies show redshift. This means that all galaxies are moving away from each other. They are spreading out, okay? So here's a table that supports, that gives evidence for both models. Please make sure you're able to state something similar in your exam, okay? So again, you can pause this video, just have a read of those points. And I've mentioned each one of them already. So we're now going to be talking about star development. Okay, so there's this phrase that we're all made up of stardust, okay, which is in fact very true. All the elements, okay, all the elements in the periodic table are made in stars, believe it or not. Okay, so everything that you see is essentially stardust, all the remains of stardust. Okay, so what is a nebula? Well, a nebula is simply a cloud of dust and gas. Okay, and the first stage in a star's development is due to gravity. Okay, this dust and gas is going to condense into one particular point. Okay, as the pressure builds up due to the friction, as the particles moving past each other, and as the gravity brings them closer together, okay, we're going to get a high temperature, okay, being built up, which will cause nuclear fusion to start. Okay, so remember, nuclear fusion is two lighter nuclei joining together. In this case, it's probably hydrogen atoms. Okay, these are light dust particles, and they come together. And as they come together, obviously, huge amounts of energy gets released, and this process can continue. So if there's more hydrogen present around, that's going to fuse with even more hydrogen nuclei. Right, so what are the differences between a protostar and a main sequence star? Well, protostars are bigger, colder, and nuclear fusion isn't happening, okay? So essentially, a main sequence star is when nuclear fusion starts to occur, okay? Protostars are essentially, you've got this effect of the dust particles still coming towards the center, okay? and when nuclear fusion is occurring, essentially you've got a huge amount of hydrogen in the center starting to fuse. Okay, so remember, we've got an inward force of gravity, which starts off the life cycle of the star, and we've also got an outward force from the pressure of the hot gases, okay, which is coming from the nuclear fusion as well, because remember that generates a lot of heat. So just bear in mind the force of gravity approximately is equal to the outward force from the pressure of the hot gases, okay, during the main sequence phase of the star. If the star is expanding, it means gravity is smaller. If it's shrinking, it means gravity is getting bigger. So as I said, but if it's stable, the forces will be balanced, and you need to be able to state this in your exam. Right, let's have a look at some pathways that original amount of dust can take, okay? So if we've got a cycle that follows a star that's similar to the size of our sun, after the main sequence stage, it's going to increase its size. It's going to swell into what we call a red giant, so which is bigger, colder, and red. So essentially, it means that gravity is a lot smaller at this stage, and as a consequence, the particles are spread out a little bit more, so it is colder. However, after some time, it will shrink back into what we call a white dwarf. So it's slightly warmer and it is white, okay? And then this can then cool even further into what we call a brown dwarf. So on the other hand, if we had a large nebula at the start, okay, so this is the sequence for a star larger than our sun, well, after the main sequence stage, it's going to increase its size into a red supergiant, okay? And then it's going to be so hot, okay? Fusion has been occurring for a very long time, which will result in it exploding in a supernova. Okay, so literally a lot of heavy elements are going to be spread out throughout space due to these supernova explosions. Okay, because they only occur at very high temperatures. Now then, depending on the original amount of matter at the start, it can either become a neutron star, which is an extremely dense star. So after all that matter has been released, the remaining matter close by is then going to come close together again due to gravity, and then it becomes simply a dense neutron star. Okay, or if that the remaining matter is so much and so dense, the star is actually going to become a black hole. Okay, so that nothing can escape from a black hole, including light. So now let's look at telescopes. Remember I said that the invention of the telescope was very important in the development of our understanding of our solar system. So we no longer believe it is a geocentric model, but a heliocentric model. Okay? I mean, telescopes are also very easy to use. Optical telescopes, anyway. You just look through them and they just literally magnify objects that are far away. Okay? Where should telescope A be built and why? Well, on the top of a mountain, away from light pollution. That's very important, away from cities. And also, there would just be less atmosphere that you would need to look through. So obviously you get a slightly clearer image as opposed to if this was literally closer to the sea. Okay. What are the advantages of using telescopes placed in orbit around the Earth? So like in image B, well, it can be used at all times. It's always dark, okay, and the atmosphere isn't in the way, okay? So remember, our atmosphere blocks a lot of different wavelengths of light, sometimes in the visible light spectrum, but you know, generally, if you're above our atmosphere, you essentially can view all the spectrums of the all the wavelengths, sorry, of the EM spectrum. So that's quite important. Okay, then finally, what are the advantages of using telescopes that detect other waves of the EM spectrum? Okay, well, essentially, you know, as opposed to the naked eye, which simply looks or can detect visible light, well, we can just see that extra bit of detail that planets or galaxies might give off if they were to, say, give off some gamma rays or radio waves, which we would otherwise not be able to detect. We can get clearer more information on distant objects if we look at their gamma waves, their radio waves, and they can be used at all times. So we can even link, telescopes up in space with a computer, so that we can actually record loads and loads of images, and then we can even send the computer some code to detect some sort of pattern that we're interested in. And so that's one advantage of using telescopes to detect other waves of the EM spectrum.